Hey guys, and welcome back. We are on our second quarter, week 3, day 2, finishing up our understanding of gravity. We're going to have our final 3 concepts to understand gravity. We started with our vocabulary words last week, and we had our first 3 concepts last week, which basically dealt with the idea that um, mass curves space-time. That was kind of the big thing, hopefully, we got from last week. And we saw this in the day 1. Here was our fabric of space-time. Here is our object with mass, and it curved the space-time. And what we can do is this is a great illustration to show how the more mass an object has, the bigger the curve that it makes. And then we can model things like orbital mechanics, the paths of orbits, where if I take this, this ball, now if I throw it out this way, ideally it would want to go straight like that. But because space-time is curved, the path of this ball also curves. And this is what we kind of saw in the previous video, was this curving of space-time by an object's mass, and how that curving affects the direction that other things will travel. The problem with this is this gives a false understanding of how space and time curve, because in this model, and if you go online and you look at a lot of pictures or in books, you see a lot of pictures of the curving of space-time, they will often show something like this, where they show space-time curving under the object, which is great for our simple brains to understand because it shows us this curvature of space-time, and we can see it. We can take our sheets and we can put stuff on it and we can see the curving, but it gives kind of a false understanding of how space-time is actually being curved. Because here's my planet, right? Space-time is being curved under it. Well, if that's true, well, let's look at this planet up close. If I'm a person standing up here, then yeah, space-time's curving down underneath. I'm going to want to go down toward that space-time. So yeah, that makes sense that I'm going to be wanting to travel down. But there are people who live on this side of the planet. But if space-time is curving under them, then they're going to want to fall off the planet, which doesn't happen. So this idea that space-time curves under the planet gives this false illusion of how it works, because basically what it would mean is everybody down here would fall off like this. Everybody up here would be fine, but everybody down here would want to fall off because they would want to go down toward where space-time is. But that doesn't happen, okay? So what we're going to look at today is a truer representation of how space-time actually is curved. So we're going to have our 3 extra concepts today. We had 3 of them last week. We're going to add our final 3 for this section today. And that's going to kind of give us our best understanding of how gravity, the thing we call gravity, really, really works. So we're going to start off with, though, looking at a very simple drawing and working from that to understand how space-time curves. So I'm going to pause here for a second and switch over to my whiteboard. Okay, so we're going to start with what we know actually happens, and then work backwards from there to kind of discover how the curving of space-time really happens. So I'm going to start here with a planet. So here's our planet, and I'm going to put people on it in different locations. So here's a person. Here's a person. Here's a person. And here's a person. Here's someone over here. Here's someone over here. And here's someone here. Okay? Now, we know, most people know that the Earth is round, that is a spherical shape. So there are people on all different sides of the planet. Now, every single one of these people feels this thing that they call gravity pulling them down. So for this person, down is this direction. For this person, down is this direction. For this person, down is this direction. For this person, down is this way. That person's down is that way. That person's down is that way. And that person's down is that way. And you can see all of their downs are pointing toward the center of the planet. Okay? So all of their downs are pointing toward the center of the planet. So everybody, no matter which side of the planet they're on, they're all pointing down. Now, some people may say, you know what, these people are right, but why are these people upside down? Shouldn't they be facing up this way too? Well, you have to understand, again, the Earth is a sphere. So if you start up here and you travel around the sphere, you end up upside down compared to how you originally were. But you don't feel upside down. Things don't look upside down because, again, your orientation, your gravity, your down is toward the center of the planet. Your head, your feet are toward the ground. Your head is in the air. So it doesn't matter where you're at. Down is always this way toward the center. Up is always out, away from the planet, away from the center of the planet. So this is what we know. We know this is how everybody around the world is oriented. Everybody is oriented this way. Their feet on the ground, their head away, and down is toward the center. So if we work backwards from that, one of the things we have to understand is, you know, we've already talked about this space-time thing, that we exist in space-time. It is the fabric of the universe. It flows around us. We exist in it. It's part of us. So what we're going to have is our first concept. Concept number, well, this is going to be number 4, because we had 3 of them last week, and we're still in the same section, so we're adding to it. So this is going to be concept 4. And this concept is that all things follow space-time lines. I'm going to put this in capital letters and underline it. Okay, so this is our concept here. All things follow space-time lines. And we say this space-time lines because we often draw space-time as like a grid. You know, like you do in math class when you draw those coordinate points and you have your grids and things like that. You have the x-axis, the y-axis, and all those lines. That's typically how we draw space-time, as a grid like that. And we are part of space-time. So whichever direction space-time goes, we go with it. Okay? So not just us, but everything. Everything that is made of matter follows the lines of space-time. So whichever way the space-time lines go, anything made of matter that's on those lines is going to go the same direction. So what we can see here is we can say, well, all these people are on space-time lines. And all of the lines that they're attached to are flowing in like this. So what we can do is we can extrapolate, fancy word, it means to work backwards, take what we know to come up with a bigger idea. We can extrapolate from this what the space-time lines are doing, because every single one of these people is part of a space-time line, and they all follow the space-time line, but they're not all part of the same space-time lines. So this person, they're on a space-time line that's doing this. This person, they're on a space-time line that's doing this. This person's on a line that's doing this. This one's on a line that's doing this. And this one's on a line that's doing this. This one's on a line that's doing this. This one's on a line that's doing that. All the lines of space-time that they are attached to are all flowing in toward the center of the planet. Okay? Now, there are more lines than this. There are lines in between them that are also doing stuff like this. Oops, that's a terrible arrow. Okay, now those are mostly just the x-axis, the horizontal ones. But again, when we draw a grid, there's also the vertical, the y-axis ones. So those would look something like this. Let's say I've got some lines up here. And you can see they kind of blend in with the horizontal ones, some of them, because they're all coming in the same direction. But some of them don't come all the way in. They have kind of this bow to them, but they don't make it all the way in. They're being pulled toward the earth, but they don't quite make it all the way. But then way out here, you can see this one's far enough away, it's completely unaffected. Let me continue those green lines out so it looks right. Oops, that one should not be doing that one. That one should be doing more like that. That's kind of sloppy, but you get the idea. So this is what's actually happening. Space-time normally is going to be nice and straight lines, like we draw our normal grid square. But objects that have mass, for some reason, space-time curves in to the object, not underneath it, like most pictures you see will show. Most pictures will show the line coming in like this, curving down underneath, and coming up like this. Now that's a great way of showing, the depth of the curve, the steepness of the angles, because that's really important when we're talking about, I want to leave the planet. Well, I have to fight my way against these curves to leave the planet, because all things follow space-time lines. These are like rivers, okay? Rivers of space-time that are flowing this way. And we are in those rivers. And we are caught in this flow, which is why we are constantly flowing down. Now, I can change which line I'm on, because there are an infinite number of lines all around us, coming in from all different directions. I can change which line I'm on. I just changed lines. I went from a line over here that was flowing down to a line over here that's flowing down. Did it again. Did it again. And again. Every time I change location, I'm changing to a new line of space-time. The problem is, all the lines I'm changing to, they're all flowing the same way. So my body wants to flow with them that way. Okay? If I jump up, what I'm doing is I'm trying to push myself against the flow of space-time. Again, imagine a river. You're in a river, floating along the river, which most of us just kind of float through life anyways, but you're floating along in the river, letting the current carry you. The current of space-time is flowing me down this way. The only thing that's stopping me from going down is the earth itself is in the way, blocking me. But I'm floating along with space and time. And then I decide, you know what? I want to be different. I'm going to go against the flow. So I'm going to jump. What happened? Well, I pushed myself against the flow of space-time, and for a very brief time, I was going the opposite direction, but then I ran out of energy. And space-time, the flow of space-time caught me again, and I followed it back down. Okay? Same way if a river. You're flowing along with the current, and you decide, nope, you know what, I want to go swim the other way. Well, you can swim for a little while until you run out of energy, and then you get too tired, and the current carries you back. Okay? This is why jumping takes energy. You're pushing yourself against the flow of space-time. Rocket ships. Now, here's a really cool thing. You can eventually get out here where there is no more flow of space-time trying to curve in. It's all nice and straight, and you can travel whichever way you want to with very little effort. The problem is you have to climb your way up against these curves to get all the way out here, and that takes a lot of energy. Imagine you're climbing a very steep cliff all the way out to here. That's why rocket ships require such big engines and all that fuel and all that big explosions and stuff, because they have to push against the flow of space-time long enough to get all the way out here. And that takes a long time. It takes a lot of energy. Okay? We can't do it as people. We don't have enough energy in our bodies. We can do it for a very brief, very tiny little bit, but then we get caught again because we run out of energy and we get caught in the flow and come back down. So concept number 4, all things follow space-time lines. And we can already see here what concept number 5 is going to be. And that is that all these lines curve in toward the center of objects that have mass. Space-time lines curve in toward the center of objects, and all objects have mass. This is a property of matter. The property of matter is that objects have mass, and this is what mass does to space-time. Mass has this weird thing that it causes space-time to bend and curve and flow into the center of an object. And because we exist in space-time, we follow, that was our concept 4, we follow those lines wherever they go. Just like we did on the stretched fabric, the fabric got curved, the ball curved with it, space-time curves, we curve with it. We follow this flow. We can go against it briefly for a short time, but eventually we're going to follow it in. So this leads us to our final understanding of what gravity is. So concept 5, space-time lines curve in toward the center of objects. So the final concept, our understanding of gravity, our final concept, our final explanation, definition of gravity is our concept 6. Gravity is the flow of space-time lines toward the center of the object. Gravity is the flow of space-time lines toward the center of an object. Okay? This is what gravity really is. Gravity is the curving of space-time and us following it. Okay? People have been talking about the force of gravity when a lot of times they say gravity is a force that pulls us. Gravity, there's the force of gravity. You hear that word force all the time, the word pull and push with gravity. Not accurate. Okay? There is no force of gravity. There is no force of gravity. There is nothing grabbing you. There is no gravity reaching out from this planet, grabbing these people and pulling them down. Okay? That is not happening. What is happening is the mass of this planet is causing space-time to curve into it, and the people are caught in that flow. So whichever direction they are on, they are following that flow in toward the center of the planet. This is gravity, the curvature of space-time and people following, or objects following, that flow of space-time toward that center. Okay, so no force of gravity. How do objects do this? How does matter curve space-time like this? We kind of have ideas. It's a very, very complicated thing. Don't have time to get into it. But there is no actual force of gravity acting on the people to pull them in. It's the curvature of space-time, people following the flow of space-time toward the center of the object. Okay, so now I've been using a planet as an example because planets are big. They have a lot of mass. So they have a big curve in their space-time, and we can feel it really, really easily. Okay? But here's the thing. I'm made of mass. Sorry, I screwed that up. I'm made of matter. I have mass. All right? So I'm made of matter, I have mass. Guess what? My body is doing the same thing. The matter of my body is causing space-time to curve and warp and bend and stretch in toward the center of me. Now, it's not very much because I'm not very big compared to a planet, but it is there. If you were to take me and throw me out into the middle of space, light years away from everything where there's no gravity and space-time is completely flat, and you were to take this marker and stick it close enough to me, my body would create enough of a little curve in space-time that this marker would eventually follow that curve in toward me. This marker is made of matter. It has mass. If you were to take this marker out to the middle of nowhere in empty space, it's going to cause a little tiny, very, very, very tiny, barely measurable curvature of space-time. Take a paper clip, stick it close. This is going to cause enough curvature. The paper clip is going to follow the curvature in toward this. This is doing the same thing, but on an even smaller amount. Everything, even an atom, as small as an atom is, even those, because they have mass, those curve space-time, little tiny bits, but enough. And anything that gets close enough to that little tiny curve that they're causing is going to follow that curve in. This is how things are pulled by gravity. They're not pulled by gravity. They're following these curves of space-time that are being caused by the mass of an object. The matter that it's made of is causing these curves, and objects flowing along are going to follow these curves, and they're going to head toward that object as if. Now, it has the appearance of a force, but it is not a force. It appears as if it is pulling things in toward it, but that is not what is really happening. Okay, so those were our concepts and kind of an explanation. I'm going to show a couple other things to help visualize this. What's going on. I'm going to look at another two-dimensional representation similar to the big stretchy cloth table, and then we'll have a short video clip that will give us more of a three-dimensional understanding, because again, this is only 2 dimensions, but we live in a 3-dimensional, technically 4-dimensional existence. So we want to see how space-time is being curved in from all 3 dimensions, all 4 dimensions, if we include time. Okay, so I'm going to do a real quick demonstration showing how this curvature happens, how this stretching happens, and then we'll look at that video clip. Okay, so similarly to the big stretch cloth table diagram, this is going to be demonstrating the curving of space-time, how that whole stretching and curving of that works. So again, this model worked in a way to help us see the curves. This is going to help us understand how those curves happen. Okay? And again, the curves don't go underneath the object, they go into the center. So I'm going to show why they go into the center, what's kind of happening. But this is only going to be a 2-dimensional model. So we're going to need to, again, imagine, if you will, this happening in 3 dimensions in kind of like all different directions. So here is space-time. You can see, it's got this grid of relatively straight lines and squares. So this is, again, how we would normally draw space-time to help us understand it. It's not like there actually really are grid lines out there, but these are what we use as people to help us understand what's going on. So normal space with no gravity, no objects out there, is relatively flat. The lines are relatively straight, okay? So what happens is you get an object that has matter, because all objects are made of matter, and all matter has mass. So what happens is that object with mass is going to take this nice straight lined grid of space-time, and it's going to do something like this. It's going to grab the space-time and pull it in toward the center. And you can see this looks a lot like that drawing I showed you, because this is what's happening. Space-time is being grabbed by matter somehow and being pulled in to the center of the object. And this is where we can see, some of these curves of how space-time was nice and straight. Now it's being curved a little bit. Some areas more than others, partly because, I'm using my hand, so I'm not getting an equal amount of pull from all directions. But it illustrates the idea of what's going on. You can see the stretching, how space-time is being stretched. So, out here, time is flowing normal. In here, because time is being stretched, it's flowing slower. Because time flows slower in this stretched area because there's more space between each unit of time. There's more space between each event that the time is measuring. So this would be like, okay, this might be a small object, like maybe, me, or an asteroid, or, whatever. If we scale it up to say a planet or a star, then you get something more like this. So the bigger the object, the more it's going to reach out and grab. See if I can grab this all and hang on to it and not lose it. The more it's going to reach out and grab, and the more it's going to distort space-time. The more you're going to see more exaggerated stretching, and it's going to reach out further to cause more stretching and farther away. So the more mass an object has, the more significant amount of space-time it's going to grab and pull in, and it's going to create much steeper stretching areas, much steeper curves for things to follow. So this is what is kind of happening. Matter grabs space-time, pulls it into itself, and creates these curves. Now, if the matter goes away, space-time goes back to its normal stuff. So let's say there's a planet flying through space. Well, what the planet is doing is as it's flying through space, it's grabbing here, and then it moves to here, and then it moves to here, and then it moves to here. And as it moves through space, every area that it moves through is grabbing the space in that area, curving it, and then as it moves on, it leaves it normal. Okay? And again, bigger objects, bigger amount of stretching because it's grabbing more space-time. So it's causing more curvature, more of this stuff here. So this is kind of what's going on with space-time. It's not curving under. It's not like, when you sit that basketball or something on the sheet and the basketball pushes the sheet down to create that curvature. It's not that. It's this. It's this grabbing of the stuff of space-time and pulling it into itself and stretching all the space-time around it to create these curves that other objects then follow those curves. And that becomes what we see as space-time. So next we're going to look at a more three-dimensional representation. Because again, this is only 2 dimensions. It helps us see what's going on from a very simple level, but it's not a true representation. So again, we really can't get a true representation because we're trying to take something that's abstract and trying to put it down into a way that we can visualize. So we got a short little video that or some clips of a video that will help us see what's going on with space-time. It'll help us visualize the flow of space-time in toward the center of an object from 2 dimensions, and then the flow of space-time in toward the center of an object from 3 dimensions, technically 4 dimensions because it's showing the time aspect also. Okay, so here's a 2-dimensional version, similar to what I was showing you with the setup that I have here. You can see here's a planet. You can see that the lines are flowing into her. As we play this and we include the time element, you can see how the lines are flowing in. This again is what gravity is. It's the flow of space-time in toward the center of an object. Now this is a 2-dimensional representation. So you can see, the flow, the time aspect as it moves in, and it constantly keeps flowing in, flowing in, flowing in. But that's only a 2-dimensional representation. So let's look at it from 3 dimensions, because again, we live in a 3-dimensional world. So here you can see this is going to be showing all around it from all different angles. And we can see the flow of space-time as the planet is just pulling space-time in toward itself. It keeps pulling it in, pulling it in, pulling it in from all sides. Top, bottom, left, right, front, back, doesn't matter. It's all being pulled in toward this. And this flow in toward the planet is gravity. And because it's coming from all directions, that's why you can have somebody on top their space-time is flowing down, so they feel the flow of gravity pushing them down this way. Whereas somebody down here is also flowing in this way, so they are also feeling the flow pulling them toward the center of the planet. So it doesn't matter where you are, whichever side you're on, because space-time is coming in from all sides, all directions, and flowing in. So this is what gravity really is. It's this curving space-time. Matter is pulling space-time in toward itself, and that flow, we are caught in that flow, and that is what we experience as gravity.